Hello, I'm Michael O'Connell, and in this video, we are going to use the Ratchford-Rice equation that we derived in the previous video to perform a flash calculation on the binary mixture of benzene and toluene. We're given that the flow rate of benzene is 4 moles per second and the flow rate of toluene is 6 moles per second going into our flash drum, meaning the total feed rate is 10 moles per second. And this flash drum is set to a temperature of 393 kelvins and 150,000 pascals for the pressure. What we would like to find is the flow rate of the liquid that's exiting from the bottom of our flash drum and the flow rate of the vapor that's exiting from the top of our flash drum, as well as the composition in the liquid phase and the vapor phase. I'm going to use the vapor-liquid equilibrium notebook that I had in a previous video for this calculation. So let's set our temperature to 393 Kelvin. Our pressure is going to be 150,000 pascals. What else do we know here? Well, we know that the total flow rate, which I'm just going to denote as S, is 10 moles per second. We also are going to need the mole fraction of each component in our feed, right? So let's represent this as Z, because I remember in the last video talking about Z sub 1 representing the mole fraction of the more volatile component in our feed that's entering our flash drum. So we can use a NumPy array for this, of course, and this will be 0.4 and 0.6, right? Because 4 divided by 10 is 0.4, and then 6 divided by 10 is 0.6. So those are our mole fractions for each component. What else do we know? Well, we can compute the ratio of the vapor phase to the liquid phase for each component, right? So we remember this as being the quotient of the pure saturation vapor pressure for each component, and then this would be uppercase T, sorry about that, divided by the pressure, which we also know. So once again, that's something else that we have in our toolbox that we can specify. We already know this before we jump into writing presumably some function to calculate this. Now, if we remember our expression here, this is a sum that is set equal to 0, and we only have one unknown value. So we can use the root solver to make this very easy so that we can find this value, V. And what is V? Well, V is going to be the flow rate that is exiting in the vapor phase, and that would be exiting from our flash drum. As we've done before, we want to create a function here, and I'll use RR for Ratchford-Rice, and we want to return an equation that we can use the root solver on. So remembering that, we have one unknown here, and I'm going to call this something random like E, okay? And that will be the first element, and obviously the only unknown we have, so the first element of the unknown vector that we're passing into our function. And then we want to return our sum, right? And again, this needs to be an array, so we'll use the square brackets there. And then we have our sum, and let's make sure we do this right. So this would be Z times K minus 1, and this is where I want to be somewhat careful here. So I'm going to give myself some more spaces, and this is going to be the numerator, so I'll put that in parentheses and divide it by whatever was on the bottom here. So V over T I'm representing as E, so that makes things a little more clear for us. So this is going to be E times K minus 1, and then this is plus 1 under there as well. And all of this there should be rather clear. So now we have our array, and we are ready to go and use the root solver to actually find our 4 unknowns. There's only one unknown that we're trying to find in this situation, and that is E. E is equivalent to this quotient in our Ratchford-Rice equation, V over T, where V is the flow rate that is exiting in the vapor phase from our flash drum, and T is the flow rate of the mixture entering our flash drum. So effectively, E is equal to the mole fraction in the vapor phase. So the root solver is going to adjust those E values until this sum is equal to 0. So we need to supply our function, RR for Ratchford Rice, and then we need to guess an E value. So as I said, it's the mole fraction in our vapor phase. So it's between 0 and 1. Let's just try 0.8. And we'll take the X attribute out of that and pull that number out of the array that it will be in. And then we can use this to find the 4 unknown values that we're after. So first, we want to know the flow rate that is exiting our flash drum in the vapor phase. We'll call that G for gas. And that is going to be the mole fraction in the vapor phase multiplied by the total flow rate that's entering our flash drum, which is S. And we have that. So we also want to know the flow rate that is exiting in the liquid phase, which is just the difference between the flow rate that's entering our flash drum and the flow rate of material that is exiting in the vapor phase, of course. Okay. Now we remember that Y, the mole fraction of said component in the vapor phase, is going to be equal to K times X. But of course we need to find X first, and we can use that using this formula here. So let me try to see if I can copy and paste this ever so carefully so as to not mess up my beautiful parentheses. Okay, so let's see what these values are, and I will discuss them and see if they make any sense. Before we move ahead, I want to talk about a couple changes I made. So I made a typo in my sum where I forgot an asterisk. So I wasn't multiplying the mole fraction in the vapor phase on the quantity of K minus 1. So I added that asterisk, and I think I added a parentheses as well over here. And I also realized that my expression for the mole fraction in the liquid phase was actually incorrect because I just grabbed it from our expression for the Ratchford Rice equation, and I forgot to get rid of the K minus 1 up here. So as you can see in this numerator, you just have Z. So I was sure to get rid of that. So I'm going to shift enter on that. And now we can look at what these values are. So G is the flow rate of material exiting in the vapor phase from our flash drum. L is the flow rate of material exiting in the liquid phase from our flash drum. And then X is going to be the mole fraction of the components in the liquid phases. And then Y is going to be the mole fraction of each component in the vapor phase. These values can be quite shocking, can't they? Because we see that the flow rate of material exiting in the liquid phase is negative, which is obviously impossible. So what that tells me is that we probably don't have any liquid phase in our mixture that is in our flash drum at the temperature and pressure that we specified. And fortunately, because we used this temperature and this pressure to generate our plots up here in a previous video, we can actually use these to see if my hypothesis that we have only vapor in our flash drum is correct. And we know that on our x-axis, we were talking about the mole fraction of the more volatile component. So for us, we had 4 moles per second as the flow rate of benzene, which would be our more volatile component. So we're at 0.4 on the x-axis for both of these plots, actually. And we can take a look at the bubble pressure and dew pressure curves on this one at a constant temperature of 393 Kelvin. So we're at 150,000 pascals. And if we go over to 0.4, we see that we are below this curve for the dew pressure, okay? And obviously we're not in between the two curves, so that means we either have all vapor or all liquid. In this case, because we're at lower pressures, we're below the dew pressure curve here, we certainly have all vapor, right? If I want to find what the dew pressure would be for a 0.4 mole fraction of benzene for this binary mixture, I would have to steadily increase the pressure isothermally until I get to, it looks like about 169,000 pascals would be the point at which that first liquid drop forms. Now let's look at this second plot where we have the bubble temperature right here and the dew temperature right here. So this time we are at that constant pressure of 150,000 pascals. So 393 Kelvin's about right here and 0.4. So if we meet at that point, we are at higher temperatures and we are not in between the two curves. And because we're at higher temperatures again, that's going to be all vapor, right? So we would have to decrease the temperature at a constant pressure in order to form that first liquid drop. So the other important thing that we have to realize is that these values that the Ratchford-Rice calculation gives us are not correct, because the Ratchford-Rice calculation that we're doing here is going to be useful when we are in between these curves, right? When we have vapor and liquid, right? Because we know if we have all vapor and we have 10 moles per second flowing into the flash drum, then that means we need to have 10 moles per second as our flow rate of vapor material exiting. So this should not be 24, right? It should be 10, liquid should be 0. So the mole fractions as well are obviously incorrect, right? There should be no mole fractions of anything in the liquid phase. And then in the vapor phase, it should just be the same ratio, right? You should have 0.4 benzene and 0.6 toluene as your respective mole fractions. So hopefully this is actually a good example for you to look at, because you realize that, hey, for this specific temperature and pressure that was given to us in this problem, the Ratchford-Rice calculation is basically just going to tell you that you don't have any vapor and liquid phase. You have either all vapor phase or all liquid phase in this case, because one of the flow rates that's exiting your flash drum appears as negative when you're coding this in Python. So hopefully that is a good learning experience for you who are watching. And obviously we can play around with this. So before I go, let's look at 0.4. So let's actually adjust our pressure to 180, because if we look at our curves here, 0.4 moles there for the mole fraction of the more volatile component at 180,000 pascals. That's between these two curves. So you should get some sort of valid calculation there. So let's see what these are. And as you can see, this works very well, right? So we see that we have 5.46 roughly. That would be the moles per second, the flow rate exiting in the vapor phase. And then you could take 10, your flow rate that's entering into the flash drum. You could subtract this from that flow rate to figure out the flow rate of liquid material that's exiting. And then we have the compositions of the liquid and the vapor phases that are in the flash drum, or, well, in this case, again, we are trying to separate the two materials so they are exiting. Obviously the vapor from the top and the liquid from the bottom in this case. But that is pretty cool. Like, it is kind of interesting that for your vapor phase, as you can see, you did not get a very good separation, right? Look at that. Almost 50% of your vapor phase is benzene, and the other 50 is basically toluene. So that wouldn't be a good separation, which is why distillations and things like that have multiple processes, right? This would just be one stage in a separation process if we were actually trying to separate a real mixture or something like that. And obviously, in a lot of chemical engineering practices, you're not going to be dealing with binary mixtures. There's going to be many, many more compounds, which is why in the previous video, when we derived the Ratchford-Rice equation, we use N up here, because it can literally be N number of components, any number of compounds that are together in that mixture that is flowing into the flash drum that you're trying to separate. So I hope this video taught you a lot, and I look forward to wrapping up this series on vapor-liquid equilibrium in the next video. So thank you so much for watching.